Hello everyone. In this section, we are going to study the motion of a particle in a disk. We will write the equations of motion for a solid particle in a disk and solve them to find the orbital change of the solid particles. As I explained, the gas drag force is acting on a solid particle in a disk due to the different rotational speed. A particle rotates around central stars, losing the energy and angular momentum by gas drag. Equation of motion in polar coordinate is expressed two equations. First equation is the equation for r direction. The second equation is the equation of motion in the theta directions. d/r dt minus d theta square over r equal gravitational force is in the right hand side is minus gm star over r squares minus f sub d vr over m times u. Drag force is directed opposite direction with respect to u. If we draw figures with the central stars and solid particles, both face of the v is the velocity of solid particles. This velocity is decomposed into the r direction and the theta directions, v sub r and v sub theta. If you consider the relative velocities with respect to gas velocities, gas doesn't move in the radial directions. V sub r, this is a v sub theta minus b sub gas and the theta direction. This is a v sub r because the velocity of the gas in the r direction is 0. Then sum of these two vectors form the relative velocity of the u. U is the relative velocity of a solid particle with respect to the gas. And drag force is acting on the solid particle. Drag force has an opposite direction with respect to the u. This is a drag force acting on the solid particle. So because of the opposite direction, we put the negative signs here and here. So we need to find out the drag force in the direction of r. Then you need to multiply the v sub r over r to find out the projection of the drag force on the r directions. In the case of the theta direction, dv sub theta over dt plus v sub r v sub theta over r equal, there is no gravities in the theta directions. Just only drag force is acting on the solid particles. Minus f sub d over m times v sub theta minus v sub gas theta over u. So we need to multiply this factor to find out the projection of the drag force on theta direction. Then relative velocities can be calculated. U square equal the v sub r square plus v sub theta minus v sub gas theta squares. Gas velocity has only the velocity in the theta direction, v sub gas thetas. And the particle velocity has a component of v sub r and v sub thetas. The rotational velocity of the gas can be calculated. V sub k is a Keplerian velocity times the square root 1 minus etas. Then we need to solve this equation. As an approximation, we consider that v sub r is very small compared with the Keplerian velocities. So very small value of the velocity is expressed with the w's. So the difference from the Keplerian velocity is expressed as w thetas. So w sub r and w sub theta is much smaller than the Keplerian velocities. We consider the velocity of a solid particle is reached to the terminal velocities. We don't have to consider the derivative of some physical quantity with respect to time to become 0. Then we use this assumption to solve the equation of motion. So equation of motion is expressed use the assumption of the terminal velocity in the r direction is a v sub theta square over r equal gm sub star over r squares plus f sub d over m v sub r over u. For the theta direction, you can express the v sub r v sub theta over r equal minus f sub d over m v sub theta minus b sub gas theta directions over u. Then we substitute v sub r equal wr and v sub theta equal b sub k is a Keplerian velocity w thetas. So wr and w theta is much smaller than v sub k's. Then v sub thetas can be calculated v sub k squares plus 2 v sub k w thetas plus w theta squares. W thetas is much smaller than the v sub k. Then the last term is gonna be ignored. Then v sub k is expressed gm sub stars over r. This becomes gm sub star over r plus 2 v sub k w theta. Then V sub r, V sub cetas can be calculated WR V sub k plus W cetas. And the product of the WR and W theta is smaller. Then we approximate WR times V sub k. V sub gas cetas can be calculated V sub k square root 1 minus etas. This is approximate V sub k 1 minus 1 over 2 eta because eta is much smaller than 1. V sub theta minus V sub gas cetas can be calculated V sub k plus W theta minus V sub k 1 minus 1 over 2 etas. So this means W thetas plus 1 over 2 eta V sub k. Then we can substitute this equation into these two equations. Then for the r, it becomes 2 V sub k W theta over r equal F sub d over m WR over u. V sub k over r, this is equal to the omega sub k. From this equations, to W sub theta equal F sub d over mu omega sub k times WR. Then if you introduce the Stokes numbers, this is equal to the 1 over st. Then this becomes WR over st. So from this equation, you can find the 2st W theta equal WR. This is the first equation. For the theta direction, WR V sub k over r equal minus F sub d over m W theta plus 1 over 2 eta V sub k over u. Then, as I explained, this is omega sub k. This becomes st W sub r equal minus W theta plus 1 over 2 eta V sub k. So we have two equations. Therefore, the relative velocity of the u squares can be calculated. W sub r squares plus W sub theta plus 1 over 2 eta V sub k squares. Then we'd like to solve these equations. So this first equation and the second equations. So this is first equation. This is second equation. The definition of the st is given by this equation. And the u is expressed this equation. Then we'd like to solve the equation 1 and 2. So equation 1, 2st W thetas equal WR. So from this equation, W theta is expressed W sub R over 2st. Then you can substitute this equation to the second equation. Then st WR equal minus WR over 2st minus 1 over 2 eta V sub k. Then we have a W sub r. Then W sub r can be calculated minus st over 2st squares plus 1 times eta V sub k. So this is the radial velocity of solid particles. Using this information, r divided by the migration speed of a solid particle, r times 2st squared plus 1 over st eta V sub k. This is the migration time scale. We discover the radial velocity of a solid particle is a negative quantity. Particle is migrating toward a central star. Then using the migration speed of the solid particle, we can estimate the time scale for the migration of a solid particles in a disk. I'd like to introduce the Stokes numbers. Stokes number is defined as a product of the relaxation time of a particle and the angular velocity. Relaxation time is defined with this equation. mu is the momentum of solid particles, and Fd is a drag force acting on a solid particles. So Fd times the time becomes impulse. So tau s is defined by the momentum divided by the force acting on a solid particle. So using this T sub s, Stokes number is expressed a ratio of the T sub s to the Keplerian times. A particle quickly follows the flow of gas when the st is smaller than 1. So this means tau sub s is shorter than the Keplerian time of the T sub k. So this means while a solid particle makes a circular motion around the central star, particle is quickly follow the motion of the gas. While the particle takes a longer time to follow the motion of the gas when the st is larger than 1. So in this case, tau sub s is longer. Okay, this is the end of this section.